we are going to go over the Weibull analysis needed for MSE 407, and we're going to go through an example. You should have already watched the background video on Weibull analysis, so that makes sense to you first, and we're going to go over a specific example relevant to this class in this video. And so to all be on the same page, I'm going to be using a lot of information from a handout that is given to you in Canvas, and I also put it on our Google Share. It's the MSE 407 Weibull Analysis PDF. This basically walks you through the procedure, which is from our textbook in ceramics, so Barsum. So you can find it there as well. But this is just kind of a step-by-step process. And then I'll also be using a data set from previous semesters. So there's actually 3 different data sets of the control glass as received from previous years, and I've compiled it into this spreadsheet here for you. So it's not one of the ones that you're using for this semester. So those are the 2 things that we're going to need for this lab, and let's just kind of walk through that Weibull analysis handout real quick. So it tells you where the material's from both an ASTM that goes over the flexural strength and also fundamentals of ceramics, which goes over the procedure for doing the Weibull analysis. So it's assuming we've done 4-point bending of at least 30 glass samples. You've recorded the diameter and the force at fracture, which sometimes we call load. That you know the inner and outer span lengths. This you should have gotten from the video on 4-point bending, and then you calculate flexural strength using this equation here, equation 1 from the ASTM, and then the next parts are going to be in the Excel sheet. So basically a detailed way of showing you how we actually perform the Weibull analysis for this material. So we are going to start out by calculating the flexural strength in Excel, and then we are going to rank with increasing strength in that spreadsheet, so that we have a ranked number from 1 up to the total number. Then we're going to calculate survival probability. This is the equation that you should have seen in the slides. So we're going to use that. Then we're going to calculate the natural log of the flexural stress in a new column, followed by negative natural log of 1 over the survival probability. And again, these 2 should look familiar. They're the X and Y from a typical Weibull plot, which allows us to plot those 2, do a linear regression, and find the Weibull modulus and the characteristic strength from the slope and the y-intercept of this graph. And so basically that's what this is going to have you do, is plot it, do a least squares fit, a linear regression, calculate modulus, and calculate the strength as well. So let's go on over to the data that I have for you. So on this data sheet, this is the raw data that we're going to use. I've numbered them, so this is just a count, so don't pay too much to this. There's also the diameter. You'll notice that most of these are right around 5. If the data didn't give me a value, I assumed 5, so they're all pretty close to that. It gives the max load, so this is the force at fracture that the spreadsheet or the PDF is talking about. And I put the inner and outer spans. This is something that you should have also confirmed from the videos. And then I've also put the tint of the glass for this to kind of show that they're one singular data set. Sort of, for now, don't pay any attention to that column. Okay, so that is the raw data. This is all the information I need to do these calculations. And so I'm going to start with taking, let me go ahead and copy this for us. All right. So the first thing I want to do is I want to use that expression from, where is it? Here. I want to use that expression up top here to calculate the flexural strength. So I need to know the force at fracture, the outer span, and then the diameter, right? So those are what I need to know. So I need to basically use this equation, integrate it into my spreadsheet. So I'm going to go ahead and just write that down so that I don't have to flip back and forth. All right, so let me go back over here. So this is going to be my flexural strength. I'm just going to abbreviate it. And this is going to be from the ASTM, you'll find that if we keep the units that they dictate, which are millimeters and newtons, this will end up in megapascals. So if that doesn't make sense, you might kind of prove that with a units evaluation there. All right, so this is in, just in case I didn't mention it, this is in Google Sheets. So you can obviously use Excel, but it's personal preference. A lot of the things are going to be very similar. But keep in mind there might be some differences. I always get paranoid about parentheses, so I'm going to use a lot of them. So basically, I'm going to put the denominator. So that was 4 times the force, and I've got the force over here, and then multiplied by the outer span in millimeters. All right, and that was divided by, for pi, I'm going to put pi and then parentheses. That's how we do it in Sheets and in Excel. And then multiplied by the diameter cubed. All right, so I hit that, and Google Sheets actually has it, and it recommends that you autofill. So I can hit this, and then all the calculations are done for me. If you don't have that in Excel or in Google Sheets that you're using, you can also just click on this square on the bottom right and drag down or click down, double click down to fill. So this gives us our flexural strength calculation for each individual broken sample that we have, right? And the one thing that you're going to notice when you look at these is the values are kind of all over the place, right? It's not plus or minus, 5 megapascals. We go from, maybe 119, and then we have some that are in the upper 200s, or middle 200s. You got the 240 or 230. So so there's quite a bit of variation, right? And that's why we need to use this Weibull approach. All right, so these flexural strengths are calculated. And so the next part in our evaluation is if we go back. So we have those, and so now we need to rank them. So what I'm going to do here is I'm going to copy all of this. Copy. And then I'm going to make a new sheet. And I'm going to paste it. But what I'm going to do is I'm going to paste just the values so that this is set. So assuming my strength calculations are set, what that allows me to do is I'm going to delete all this other stuff. And I'm just going to be left with the strength and then a number. And in fact, the number is not going to matter. But what I want to do is highlight this data set. And what I'm going to do is I'm going to go to data, and I'm going to sort. So you can also do this in Excel in a similar method. And I'm going to sort it by the flexural strength, which is column B, but we also have a header included. So I'm going to say data has a header row, right? And so it labels it. And then this is going to filter it or sort it from smallest to highest, which is what we want. So you see now I have the lowest here, all the way up to the highest down here. The numbering's mixed up now, so we don't care about that numbering system. So basically I'm going to reorder this, because that's what the directions called for, is to number it from 1 to whatever the highest number is, with increasing strength. And so that's what I've done here. And you'll also note that I have 33. All right, so that was the next step. So I've ranked it, and I've sorted it, and I've given it number 1 to N, and N for us is 33 in this example. Your example might be slightly different, and so keep in mind that number. So the next thing I'm going to do is I need to calculate the survival probability, and that's this equation. So again, I'm going to jot it down so that I don't have to swap back and forth. And I'm going to go to my expression, and I'm going to make a new column, and I'm going to call this S and then sub J. And this doesn't have units, so I won't put any there, but it is 1 minus, and then same thing, you'll notice that I always use a lot of parentheses, so I'll put those in for the numerator and denominator. And so here, it asks for J minus 0.3, where J is the number of the sample, so that's where you're going to use this value. So that's why you want to order them. And then minus 0.3, and then the bottom is the total number, capital N, and so I can basically go down here to the last one and click this one, but I don't want this changing when I try to fill this formula, so I do that, if you're familiar with this, by putting dollar signs before and after the letters. So that fixes the position of this. So this will always be the 33. You could also write 33, but this is just another way of doing that. All right, and then I needed to plus 0.4. So that was my expression for the survival probability. And again, I'm just going to use the autofill this time. So let me kind of bring your attention to this. So this is the survival probability. So what it's saying is that if I have a stress value of 103, it's going to survive 98% of the time. If I have a value of 162, right, the probability goes down to 56, right? That's what it's telling us. So you should always keep that in mind. The lower the value, the higher survival probability should be. And then the higher value, the lower this should be. So if we bring up the force on the glass rod to 242, roughly, it only has a 2% chance of surviving, or 0.02, right? So that's what this is giving us. So you can always do a sort of sanity check. Lower the number of strength, the higher the probability should be if we're looking at survival. All right, so we've got that. Let's go back and look at what we want to do next. So the next couple things are basically to calculate a couple things, and it's just simple calculations. So natural log of the stress, and then negative natural log of 1 over S, the survival probability. So we're going to do those two in the next round, and I've jotted those down. So I'm going to call this natural log of sigma, and this is equal to, as you might guess, natural log of this value, which is sigma. All right, and same thing, I've calculated it here. It doesn't have units inside of a natural log, and then I autofill so that I can calculate all the values. And then negative natural log 1 over S. It doesn't like you to put negatives in titles, so I'm going to put a quotation here, and then call it 1 over S, and S sub J to be more straightforward. Okay, and then again, this is a simple one to get as well. I'm just going to put that expression in, a double natural log, which looks funny, but that's what we have, and then 1 over, and then the S sub J here. All right, and then autofill again. And so we got all of our expressions here that we need. So let's go back and just kind of see what it wants us to do next. So we're going to plot, and we're going to do it such that we have, this is the Y and this is the X. so that we get something comparable to this plot here, so that we can do a least squares fit, and then we're going to calculate the modulus and the characteristic strength. All right, so let's go back and just kind of work on the plot. So I actually had you fill it in this particular order because if I just select both of those columns and I go to, I believe here it is, insert chart, it's going to be something similar in Excel. So if I do that, it will produce a bad plot. But what I'm going to basically do is I am going to let's go to, sorry, oh, here we go. So if you go to setup, there'll be a chart type, and what you want to do is with all of these types of experimental data, you want to use scatter, because each one of these wants to be a point, and then we're going to add a linear fit to it. So let's put that in there. And so again, I'm not going to be too worried about what the data looks, or what the plot looks like at this point, because I just want to do a fit. But this is our plot. And again, if we kind of go back to the plot here, you see that it has a similar trend such that we have a negative of the Weibull modulus. So we have a negative slope here. And so that's what we're getting here. All right. So in Excel and in this, we can have, we can right click on the data series. Let me do that again. If we right click on it, we can typically add, okay, so this is something that you can do in Excel. You can right click and then add a trend line. Here for this one, I'm going to double click so I get back to this chart editor, and then go down here to format data point. Below that you see a trend line, and so we can add a trend line, and the default's going to be linear, which is good because that's what we want to do. I'm going to color this green, red, so you can see it a little bit better. And then for a label, we want, what I want to show you is the formula, so the equation. And then I also want to put the r squared there as well, so you can see how good of a fit it is. All right, so let me exit out of this and get back to here where you can see it a little bit better. So you see the fit here. It's pretty good in the middle. There is some variation on the extremes, very high and very low, very high and very low. So that's something to keep track of, that those points are a little bit different. But if we look at the fit's pretty good. The closer to 1, the better. And so this is 0.97, so that's quite good. It could be better, but for now we're going to take that. And then our equation here is, this is y equals minus 6.2 times x plus the intercept. So it basically gives us the slope and the intercept here. And so we could jot those down. One thing I don't necessarily like about the plots when you do it like this is that it's not easily copy and pasteable, because you basically just have to write it down. So another thing that you can do is you can come back over here, and let's say we want to calculate the slope. So instead of doing it here, what we can do is we can use the equation slope, and what that does is so if you use equals slope, you're going to take the y and then the x. So this is the y data. So you're going to take the whole series of y data, which is this, and then the whole series of x, comma, the whole series of x data, and calculate the slope. And so you'll see here that it calculates, it's a negative 6.185. And so it's basically the number here. And so we can do the same thing with the y intercept. There we go. And this one is, I think, int. Nope, intercept. Here it is. If you don't know, start typing it and see if you can figure out what it is. I believe it's either yint or intercept for in Excel as well. But again, keep in mind that the equations might be slightly different. But I can do that. And You can also click this if you're wondering how to do it, right? It'll give you an example of how to do that as well. So it wants the y data first and comma the x data. And so I will use that. So my full y column and then my full x column, and hit that. And so it's going to give me the 32.15, which again is the number over here. So it's just a way where now we can just copy and paste this value. And so what I'm going to do now is let's go ahead and calculate the values that we care about, right? And so this goes back to the formulas that you saw in the background video, as well as in the sheet as well. So let's go with Weibull modulus. So you saw here that the Weibull modulus is in fact the negative of the slope, right? So if I go back, it's equal to negative the slope. So again, I can just set up this function to do that. So simple, nothing difficult. You can tell what it is, but just to get rid of the negative. And then the characteristic strength, and this will again be in megapascals because that's our base unit. And so for this, we need to go back to the Excel sheet, or sorry, we need to go back to the slides for a second. So I'll transition over there and show you how we're going to calculate the characteristic strength. All right, so we're trying to get our characteristic strength, which again, keep in mind is the sigma naught value. And so it's going to be tied to the y-intercept. So our y-intercept is b, and that equals m natural log of sigma star, right? So basically we just need to rearrange this. So if we take the y-intercept and then move the m over, then we get natural log of sigma star. So this will give us, taking the y-intercept divided by the modulus will give us the natural log of this characteristic stress, but we want to take the exponential of both sides so we can just get the stress value. So this is unitless, but this should be megapascals. So if we take exponential of both sides, we get sigma star equals exponential of b over m. So this is the equation which we're going to put into our Excel sheet in order to calculate this. And again, keep in mind that this value is where our y value is equal to 0. So in the slides I kind of showed you that that was equal to 0, but if you set that up, this is also how you would get characteristic strength directly. All right, so that's what we're going to put into our sheet or Excel sheet. So I'll switch back over and we'll complete that. And finish off these calculations. So we're trying to get the characteristic strength. You just saw the equation for how we're going to do that. So it's going to be the exponential of the y-intercept, which I have right here, divided by the modulus, which I have right here. And if I do that, I get a value of 180.8. One thing I typically try to do as well when you finish doing these calculations, keep in mind that this is way too many significant figures for these calculations. And so I try to minimize it just so that you can kind of see a little bit better what these values are. So again, our characteristic strength is 180.8 megapascals. So again, this is kind of a measure of our strength, our kind of similar to the average in Gaussian statistics. So we can compare, and again, remember that this is a strength at a given probability. So we can compare that across series to compare strengths of different glass sets. Then we have the modulus, which is an indication of how tightly clustered together that data is. So this is 6. If we have a value of 12, much higher value, that data is much more clustered together, and because again that was the shape factor, so it's a much more narrow distribution, as opposed to 3, which would be a much lower number. It's a very broad distribution and the values are spread out quite a bit. So the idea with these numbers is that we can calculate these two parameters from the Weibull analysis, and we can compare strengths to other data sets, and we can compare the packing or the closeness of the data using the modulus. And so that's what we're going to do to all our data sets in the lab. As each data set, we're going to run the Weibull analysis, and we're going to get these two parameters, and that will allow us to make comparisons and therefore conclusions about the data and what occurred during ion exchange, etc. All right, so this is how you do this analysis. Beyond this, make sure you're always looking at the data. So even if you use these formulas to calculate slope and y-intercept, I would also add in an r squared to that calculation, and I believe it's r square. You can see it there. And the same thing, you want to do it for this data. And again, on this one, I mentioned that the r squared was pretty good, but it could be better, right? So these portions are here. So you in your write-up, you might want to think about what these values mean, and therefore be able to kind of discuss why there's some variation. But the other thing is definitely plot this data, because you want to see where the sort of anomalies are coming from. And so you want to see if the data is at the far end here over on the right, or up here, or if it looks like there's multiple slopes. That's the kind of thing you want to check. So r squared will tell you how close, but it's very good. You should always be plotting so that you can see how good of a fit you have and where there might be deviations from what you expect. So always take a look at that when you're looking at your Weibull data.